Welcome back, nerds. Section 6.2 is what we're talking about now. Talking about inverse relations and functions. Now, we've already discussed inverse functions and inverse relations in this year. We did it way back in chapter 1, a long time ago. And that's when we were talking about things being functions, passing the vertical line test, things being one-to-one, which meant you had a function and its inverse was a function, which meant you had to be passing the vertical and horizontal line test. And we did all that. But we didn't do anything algebraically with it. We just worked with the graphs and talked about what we could see and things like that. So now we're going to start working with the algebra of inverse relations and then hopefully functions as well. So this blocks you have here in the top of these notes is mostly review. There's only one line in it that's new, and that one line is at the end. So I'm just going to put a little star next to it because that's the one we're going to be, that's new for today. So that's the one we'll be practicing, but we will utilize a lot of the knowledge in the box. So what all is going on here? First of all, the word relation, I should probably define that. What is a relation? A relation is any equation that has x's and y's in it. You're literally relating x's and y's. An inverse relation is a rule or an equation that maps the range of a function back to its domain. What that means is an inverse function will basically undo all of the operations that your original function did to an x value. So your original function might double an x value and then subtract 5. Well, the inverse would undo those operations in the reverse order and give you back what you started with. An inverse relation is the reflection of a function over the line y equals x. That's a big deal. We're going to call that the reflection principle. This is the same result as just switching x and y for every single coordinate. We're going to do that again today. We did it way back in the day. We're going to do it again today. We're going to get x comma y's, we'll switch them and replot them. That has the result of turning your paper 90 degrees. That's what it looks like. Not your paper, your graph. If an inverse relation happens to be a function, then we can actually call it the inverse function. And the symbol we use for inverse function is f with this little -1 superscript. This is not an exponent. Don't say f to the -1. No, this is said f inverse. Cool beans? So if you have an f of x, you can have an f inverse of x if its inverse is a function as well. If you have a function and its inverse is a function, then you could say the original f is 1-to-1. That's old material. Because switching x and y has the same result as turning a graph on its side, we can use the horizontal line test on a graph to let us know if its function will be, if its inverse will be a function. Because, you know, we look at a graph and we go, hey, if that passes the vertical line test, it is itself a function. So then if you turn your paper sideways, you could then check to see if your graph passes the vertical line test. Or you could just say, well, I don't feel like turning it sideways. I'll just use the horizontal line test and just say, if this horizontal line can't touch my graph twice, the inverse is a function. So all of that's old. The only thing that is new for us today is how to find the equation of an inverse algebraically. Now, I've already said it a couple different times. You're going to switch x and y. Well, you will literally switch the x variable and the y variable and then do SADMEP, get y by itself, solve for y. If it's a function, you'll say f inverse of x. They're not always functions. But if it is a function, you'll say f inverse of x. But yeah, switch x and y, get y by itself. It's really not difficult. Before we go to actually calculating any of these inverses, let's look at these three functions. And all three of them are functions. What we're going to do is we're going to try to figure out if the inverse is also a function and how you know. Okay. This is a linear equation. This is not a horizontal line. I hope that's obvious. You could pass as many horizontal lines as you want to through this thing. Every single horizontal line, if you look at they're going to hit this graph a single time. So because every horizontal line hits this graph a single time, we could say it passes the horizontal line test, which means the inverse is a function. That's old. We did that way back in chapter 1. This is a quadratic. Not that it matters too much, because it's a quadratic, but it points up because the front number is positive. I don't need the actual graph, I just need to know what it looks like. Hopefully we can all agree that it looks something like that. This is a function. It passes the vertical line test, but check this out. Boop. This is a horizontal line. Oh boy. This horizontal line hits my graph twice. This fails the horizontal line test. So the inverse is not a function. There is an inverse, but it's not a function. And then probably the hardest one of the three for students to really have a deep understanding of what's going on is this one. Here's what you don't want to do. You don't want to have to plot these coordinates. Worst case scenario, you have no other way of knowing, all right, fine, you can go ahead and plot the coordinates. You don't want to have to do that. You don't want to have to plot the coordinates to see if it passes or fails the horizontal line test. That's too much work. Instead, what you want to do is you want to use the definition of a function and the definition of an inverse function. So I'm going to come up here and I'm going to add the definitions to these notes. What does it mean for something to be a function? It means for every x, there is exactly one y. And that's why we use the vertical line test. Because every vertical line is x equals some number. And if a vertical line can only touch your graph once, then you go, oh, for that x value, there is only one y value because it only hits the graph once. Okay? For every x, there's exactly one y. That's what it means to be a function. So since inverses switch x and y, in order for you to say that the inverse is a function, you literally just switch the x and the y. For every y, there is one x. There. Now we can look at this tiny table. Verifying that it's a function. I was already told it is. Verifying it's a function. Do any of my x values repeat? No. Since none of my x values repeat, then I don't have to worry about this rule being broken. If an x value repeats, is it a guaranteed problem? No. It's not guaranteed. But that would be what you would be looking for. So because for each of these x's, there's exactly one y, I know it's a function. For each of these y's, is there exactly one x? Well, what you actually have to do is, again, look for repeats. Do any of the y values repeat? Yes? Then that's where we need to focus our attention. Just because a y value repeats does not mean we have an automatic issue. It just means this is what we need to pay attention to. So let's look at the x values associated with those y values. What I'm seeing is when y is -1, I have x is -1. When y is -1, I also have x is 3. So for every y, do I have exactly one x? Nope. For this y, I have two different x's. So because this y has two different x's, it is going to break the definition of an inverse function. Not every y has exactly one x. So the inverse is not a function. In period 1, they asked for a little bit more information, different kinds of examples. So what I did was, and you don't have to have this written down, I just wanted to make sure it made its way to this video, I drew up a couple different examples, okay? Can I cover this with a piece of scrap and write these? Okay. Like I said, you don't have to have these written down, I just want you to see it happen. Gonna draw up a couple different XY tables. This one I did 0, 1, 2, 1, 4, 5, and 2, 3, negative 1, 3, 8, 2. Okay. First, let's see if it's a function. For every x, there's exactly one y. The only thing that you need to look for to see if it breaks that definition or not is, were there any repeated x's? Oh, there was repeated x's. I have an x repeat right here. So then what you have to do is look to the y's. For x equals 1, do I only have one y value, or are there two different y values? Oh, these two are the same? Then we're in good shape. This is a function, because for every x, there was exactly one y. But that's what I would have been looking at to see if it broke the rules, because it was a repeat. Oops. I missed a negative sign. That would have changed this example. Now look at the y values. I wonder if the inverse is a function. Do any of my y values repeat? Well, yeah, they do. In fact, they're already circled. So since they repeat, you would go, all right, let's see if it breaks the rules of the inverse being a function. For this y value, are there more than one x values? No, there's not. So for every y, there's exactly one x. So the inverse is a function also. Okay, how about a different table? This time what I'm going to do, I'm going to write out the exact same table. Well, I'm going to write out nearly the same table, two small changes. All my x's are the same. 0, 1, 2, 1, 4, 5. My y's, I'm going to go 2, 3, negative 1, 0, 8, positive 2. Let's see if this is a function. For every x, there needs to be exactly one y. So we look to see if we have a repeated x anywhere. Uh-oh. I have a repeated x right here. As you saw here, that's not a guaranteed issue. Now that we've identified where our x's repeats, let's see if they have exactly the same y value. And, uh-oh. For one of my x's, I have two different y's. Well, that doesn't make any sense. If x is 1, there should only be one y value. But since there's 2, we could say this is not a function. Interesting. Its inverse might still be a function, though. Let's look. Let's see if the inverse is a function by checking to see for every y there's exactly one x. Okay, so we're going to go through our y values, and only thing we're going to have to look for is a repeated y value, because that's where we might encounter an issue. And yes, there is a repeated y value right there. That doesn't guarantee we have a problem. Let's look to see if they have the same x value. For y equals 2, do I have the same x value? Nope. That means the inverse is also not a function. Now, I could change a couple things to make the inverse a function if I wanted to. I could scribble out this 5 and put a, I don't know, -1. Wait, what am I talking about? It's 0. Has to be a 0. I'll be okay. There we go. Now the inverse is a function because the repeated y value gives me back the exact same x value. Now the inverse is a function. You see, so there are times when they're both functions. There are times when they're both not functions. That's 2 thumbs down. There's times when the first one's a function, the second one's not. And there's times when the first one's not a function and the second one is. The point is I could come up with all 4 combinations using a table. We just need to know the definitions and what to look for. Look for repeated things and then look to see if they break the rules. Okay? Just because you have a repeat is not an automatic rule break. First, we're going to determine whether or not the inverse of this is a function. This is a linear equation, just like this graph is a linear equation. And because this linear equation is not horizontal, it's going to pass the horizontal line test. So the inverse is a function. Okay. If an inverse exists, it does, find the equation of that. Then we're going to graph both things. So how do we find an inverse algebraically? How do we find it by hand? Switch x and y. And then we're going to try to get y by itself. So I'm going to switch this x and this y. Now it's time to solve for y. Get y alone. Subtract 4. Remember, when you're trying to get something by itself, you have to use PIMDOT's reverse order. You have to use SADMAP. Now I'm going to have to divide everything by -2 to get that y all by itself. Everything by -2. And I'm going to write y equals x over -2. Since I have to graph this, it'll be easier to call it -1/2 x. And -4 over -2 is +2. And we've already said that it itself is, this original one is a function, and the inverse is a function. So what do we have? We have our original, oh, I threw my pen. We have our original, we'll call it f of x is -2x plus 4. And then we have our inverse, we'll call it f inverse of x is -1/2 x plus 2. We're going to graph these 2 straight lines. And I have a straight edge buried over here somewhere. There we go. The purple one first. Well, they're both in slope-intercept form. The purple one has a y-intercept of +4. And then it has a slope of -2. That's down 2, right 1. Down 2, right 1. There you go. I need 3 dots. That's enough. I'll connect them now. There is f of x. Now, f inverse in red. It has its y-intercept at +2. And the slope is -1/2. That means down 1, right 2. It's down 1, right 2, down 1, right 2. Those 3 dots are enough. There it is. There's f inverse. I would like for you to see something. I'm going to turn my paper just a little. there's the line y equals x. Notice that the two graphs, f and f inverse, intersect each other at y equals x. And notice that these two upper pieces are reflections of one another. These two lower pieces are reflections of one another, meaning the red line and the purple line are reflections of one another over the line y equals x. The reflection principle is holding true. Also, look at this. The purple y-intercept was 4. Well, x and y have to switch places, right? That's why the red x-intercept is positive 4. The red y-intercept is positive 2. Well, x and y switch places. That's why the purple's x-intercept is positive 2. Every single purple coordinate, all you have to do is switch its x and its y to get a red coordinate. Just to prove a point, here's another one at -1, 6 in purple. -1, 6 in purple, 6, -1 in red, switching x and y. Isn't that neat? What do you think? Can you pull that off? Can you switch x and y and use SAD-MEP to get y alone? Yes? No? Maybe? Do you understand the whole switching x and y being a reflection over the line y equals x idea? The reflection principle? That makes sense? Some of you are paying attention? Okay. All right. Great. Now, woohoo. Next. Look at all the space we have for this question, and we are going to use it. So, unfortunately, not all functions have a single inverse. And that's because in order to have a single inverse, you need to be able to pass the horizontal line test. Well, you saw a quadratic fail the horizontal line test, which means the inverse is not a function. That doesn't mean you don't have an inverse. No, there's definitely an inverse. It's just not a function. It's a sideways parabola. But mathematicians are obsessed with functions, and they want things to be one-to-one. So you go, okay, how can I make it so that this quadratic has an inverse that is a function? And there's a way. The way we do that is we split this in half. We call it two different functions. And then we say each of those two functions has its own inverse. And we split it in half using its domain. So we cut the domain in half. So we could say the left half of the graph or the right half of the graph. Because you notice if you only have one half of the graph, it's going to pass the horizontal line test, isn't it? Now the inverse of that is a function. The inverse of that is a function. But they're two different inverses. It requires us to restrict our domain. All right. So here we have a quadratic. It's in standard form. It says find the inverse relation algebraically. And I do have to say relation because it's not a function. At least not one function. Okay, well, here's what's up. You don't want to find the inverse of any polynomial unless it's written in what we would call a vertex form. We're never going to try to use standard form. It doesn't work. It's not pretty. So we actually need vertex form. We need vertex form if we're going to find the inverse relation. Well, there's two ways to get vertex form. We did them both in last chapter. You could do it the technically, correct math way, and that is by completing the square. Or we could get it there in a much faster, easier way as long as you remember the steps. It's completely up to you. Either way, get it in vertex form. I don't feel like completing the square this morning, so I'm not going to. Instead, I'm going to say, well, if I need vertex form, why don't I just find the vertex? And then use the same a value that this has, especially since a is 1. So I'm going to track down my vertex. I need axis of symmetry first. X equals negative b over 2a. That's how you find the axis of symmetry of standard form. So negative, my b value is 6. My a value is 1. I've already said that. Negative 6 over 2 is negative 3. I know that my quadratic has a vertex at negative 3 comma some y value. How do we get that y value? Yeah, you're going to plug in negative 3. We're going to find out what f of negative 3 is. Let's figure that out. That means everywhere f had an x, we're going to open a set of parentheses, and in those parentheses, we're going to drop that negative 3. This will give us the y value of our vertex. Negative 3 squared is positive 9. 6 times negative 3 is negative 18. Plus 8, 9 and 8 makes 17. 17 minus 18 is negative 1. That means the vertex of f of x is at negative 3 comma negative 1. And we already know a is 1. Just going to remind you what vertex form is up here. We know a is 1, and we just found h and k. We just found them. So our original function, right in blue, is a1 x minus negative 3 quantity squared plus k. There it is. Our original function. Those are the same. Okay, that's old. That was last chapter. Vertex form. Ta-da, we converted. Yay. Now, though, we could switch x and y and find the inverse function. Excuse me, inverse relation. I'm sorry. The inverse is not a function. You just have to remember that this is a fancy way of saying your y values. So let me go ahead and switch my x and my y. There, I switched x and y. Start getting y by itself, following PEMDAS in reverse order. We have to follow SAD MEP. Getting that y alone, SAD MEP. First thing I do is add 1. Y is stuck inside a set of parentheses that have a square on them. How do I get rid of squares again? You guys can just shout it out. Square roots. Okay. We have to take the square root of both sides. And what do we already said they get rid of each other, but what do we have to remember to do when we cancel a square with a square root? Plus or minus. Plus or minus, that's two different things. Plus or minus the square root of x plus 1 equals y plus 3. You get y alone by subtracting 3 from both sides. Now you don't know y yet, but put that minus 3 to the right of the radical. And I'm just going to flip them over because I like my y's on the left. We get y equals 2 different things. Positive square root of x plus 1 minus 3, or negative square root of x plus 1 minus 3. Our quadratic has two different inverses. And they're both functions. But if I tried to call it one graph, it's not a function because it's a sideways parabola. Alrighty, look, you don't know how to graph square root graphs yet. That is this chapter. We're doing it this chapter. You don't know how to do it yet. So, oh my gosh, what do I do? I tell you what you do. Use the reflection principle. You know how to graph quadratics? We spent a lot of time doing it last chapter. We're just going to get a whole bunch of x comma y's for this graph, and then we're going to switch those x comma y's to get these graphs. But, because I know what's coming up, what I'm going to do is I'm going to graph my quadratic in two different colors. I'm going to graph this in two different colors, and I'm going to graph these in two different colors. All right? And let's see. I'm trying to pick the colors I want to use. I'll use orange and blue. We'll use orange and blue. Orange and blue are always really good. And we know we're going to use our reflection principle, right? Actually, you know what? I'll draw that line in a moment. Let's graph this thing. We said its vertex is at -3, -1. There's -3, -1. All right. Now I'm going to graph the right side in blue. I'll graph the left side in orange. You know the two sides of the quadratic are reflections of one another over the axis of symmetry. Okay. So we're going to do this verbally. I'm not going to show the work for it, but I'm hoping that you can easily pull this off. I'm going to take -2, and I'm going to figure out what my y value is when x is -2. -2 plus 3 is 1. 1 squared is 1. 1 minus 1 is 0. Its reflection over the axis of symmetry is there in a different color. Now I'm going to use x equals -1 because that's the next x value. -1 plus 3 is 2. 2 squared is 4. 4 minus 1 is 3. Its reflection is here. And just to have one more point, let's find the y-intercept when x is 0. 0 plus 3 is 3. Oh, I'm shaking like a leaf. 0 plus 3 is 3. 3 squared is 9. 9 minus 1 is 8. My y-intercept is 0, 8. Its reflection is here. Now I'm going to draw my quadratic to the best of my ability. There's the blue half. And here's the orange half. I'm going to take my straight edge now, and I'm going to put the line y equals x on here as a dotted line because I know that that is my reflection line to get the inverse. There we go. I'm going to take all of my blue coordinates and I'm going to switch x and y. And I'll graph it in blue still. The vertex was at -3, -1. Switch x and y. -1, -3. -2, 0. Switch x and y. 0, -2. -1, 3. 3, -1. 0, 8. 8, 0. Take all your orange dots, switch x and y. -4, 0. 0, -4. -5, 3. 3, -5. -6, 8. 8, -6. And I draw quadratics better upside down. I should have just turned my paper before. There. And here's what I want you to see. The two blue graphs are reflections of each other over that green dotted line. And the two orange graphs are reflections of each other over that green dotted line. That means my two blue graphs are inverse functions of one another. My orange graphs are inverse functions of one another. These are these. Which one do you think is the blue one? The positive radical or the negative radical? The positive radical is the blue one. So this one was blue. This one was orange. So then what do? What we do is we say that the blue one is the inverse of f of x when specifically x is greater than -3, because that gets me just that half. And we say the orange one is the inverse of f of x when x is less than -3, because that would give me the orange half. So we're going to do it like this. I'll do orange first because it's to the left. F inverse of x equals negative square root of x plus 1 minus 3 of f of x when x is less than or equal to -3. Let's be really clear here, though. This graph isn't using this domain restriction. This is a domain restriction of the original parabola. I'm saying the left half of the parabola is this orange graph. And then I could say that the right half of the parabola is the positive square root graph. And the right half requires x to be larger than -3. Mr. M, you included the -3 on both things. You're right, I did, because it doesn't matter. You get to pick which one you want to go with, and I'd rather just say it goes with both. Now, because we don't know how to graph the square root graphs on their own just by using their standard form yet, which we will very, very soon, but because we don't know how to do that yet, we have to do this the hard way. This was the hard way. There is an easier way to restrict the domains, but it requires us to understand these graphs a little bit more. So we'll get to that later in the chapter, and we'll revisit the idea of restricting our domains. Okay? We'll revisit that idea. Now, one more thing I want to point out is an idea about inverses. These are domains of f of x. Yes? Can we agree that these are domains of f of x? I'm using the left half of the domain or the right half of the domain. But I would like for you to look at how the number -3 is used for this. -3 is a y value. These domains of f of x those are the ranges of f inverse. The range of this blue graph is y is greater than or equal to -3. The range of this orange graph is y is less than or equal to -3. So why did that happen? Because we switched x and y. All the x's, the domain, became y's, the range. All the y's, the ranges, became x's, domain. So switching x and y switches the domain and the range as well. It's just a neat idea. It's a good concept. That's a really long problem. There's a lot of understanding going on here. And I would wager that there are, or should be, a considerable number of questions in the classroom. You guys want to ask me anything? No? Okay. Since nobody's asking me anything, tell you what we'll do. I'll make one up. And we'll see if we got it or not. Uh-oh. I don't think I have time for that, do I? I don't. We don't have time. Tell you what. Since we didn't finish the notes, the homework's not due tomorrow anyway. I always plan on this lesson taking me 2 days. We'll start tomorrow with that question that I was about to ask you. Okay? For now, we're good. Thanks, nerds.